Alright, so in this video I'm going to talk about, or we're going to address the question, where does the normal curve come from? So we hear a lot about the normal curve, aka the normal distribution, aka the Gaussian distribution, aka the bell curve, and it seems like that curve is everywhere. Lots of variables have a distribution that is at least very similar to the normal curve, if it's not perfectly normally distributed. And so why is that? We're going to ask that question. What does a normal curve mean? When we see that in data, what should that make us think of? All right, and to do that, we're going to start actually quite a bit simpler than that. So to get an idea of why so many things are normally distributed, let's imagine a variable that has just 4 things that cause it. So you can think of it as being like a genetic trait or something like that, but the principles we'll develop will apply to anything, really. Let's imagine there are 4 causes of this trait, and that each one can only do one of 2 things. It can add 1 to the trait, or it can add nothing to the trait. Right? So, 4 causes. Cause 1, you get one of 2 versions, a 0 or a 1. It's going to add 1 to the trait, or it's going to add nothing to the trait. Cause 2, same thing. It adds 0 or it adds 1, and so on. So, to make things simple, let's imagine that they all have equal probability and that they get shuffled randomly. So we can write out everything that can happen with all 4 causes, although it's a little bit cumbersome. But remember back from the probability videos that this is our sample space that we're talking about here. So one possible thing that could happen is that you could get all zeros. All 4 causes line up 0. You get straight zeros, and so the value for the trait, whatever this is going to be 0. Alternatively, cause 1 might be a 1, but all the other 3, causes 2, 3, and 4, all line up 0. You see how this is a lot like coin flipping, right? Heads or tails, right? And of course, here are all the other possible outcomes of this experiment. So if we list out every possible combination of these 4 causes, there are 16 possible outcomes. And of course, that's ugly to look at. We don't want to look at that. So we want to draw a picture, maybe, of the frequency histogram. And of course, that looks like this. And so what you can see here, if we look at the frequency histogram of all the outcomes, we see something that shares a lot of the traits of the normal distribution. Now, of course, many of you will recognize this distribution as the binomial distribution for 4 trials, and equal probability of the 2 outcomes, P equal to Q equal 0.5, like a coin flip. But the important thing here is that very few of the possible outcomes are very small, like 0 or 1. Very few are very big, like a 4. And most are middling, or near the average. Most of them collect in the middle. And you can see the reason. It's very unlikely that all the causes, or even most of them, will align to make the trait really low, and it's also very unlikely that they will all align to make the trait really high. In most cases, some will come up low and some will come up high. Just like in most cases of flipping a coin 4 times, we get some heads and some tails, and only rarely do we get a long run of either heads or tails. Now, just imagine if instead of 4 causes, we had 10 causes. And then imagine that if that instead of only 0 or 1, each cause was itself a continuous variable, so that it could be 0.5, 0.97, 1.4, 3.5, and so on. So we have 10 causes, and they aren't just 0 or 1, they are a continuous variable. We now have an infinite number of possible combinations. Each cause contributes just a little bit to the overall distribution, and again, the chances are very low that most or all of the causes will align low or align high. Most of the time, some of the causes will contribute to increasing the trait, and some will contribute to decreasing it, so that most instances of the trait are middling, in the middle. This is where a normal curve comes from. And of course, in real life, most of those causes are themselves normally distributed because the causes are themselves caused by lots of more or less independent things. But as in our binomial example, or as our binomial example shows, the underlying causes do not have to be normally distributed in order to generate a normal distribution. Most distributions, if combined with lots of other distributions, will create a normal distribution. I had probably been analyzing data for 8 or 10 years when I really stopped to think about this stuff and what it meant. One thing it means is that if you have a variable that is normally distributed in the population, you probably shouldn't bother looking for a big effect size of your causal variables, because your dependent variable, the variable that you want to find the causes of, has lots of causes, so none of them can be very big. An example from my own work is reaction time. How fast somebody can react to a stimulus. At one level, it has a few dozen conceptual causes, like perception, attention, memory retrieval, response planning, response execution. That's the psychological level. At the neuronal level, it has hundreds of millions of causes, the current state of each of the millions of neurons involved in the response to the stimulus when the stimulus happens. Okay, so looking for big effect sizes is out. What does that mean? It means you need to use bigger samples, and you need to really pay attention to how you measure your variables, because causal effects, which are probably going to be small, can easily hide behind the measurement error. This is one of the reasons you can't infer that the null hypothesis is true when you get a null result. With a bigger sample and more precise measurement, you might be able to detect the effect of the causal variable that instead gave you the null result with your too small sample or your too noisy of measurement. All right, well, that's enough for now. When you see a normally distributed variable or an approximately normally distributed variable, think lots of causes and think, of necessity, small effect sizes. If you're getting a big effect size for one single predictor of a normally distributed variable, chances are it's because that predictor is the same thing as the variable you're trying to explain. In other words, they are really collinear. You're measuring the same thing in both cases. Anyway, that's enough for now, and we'll catch you next time.